Hello, IB. You guys are getting into domain and range, hopefully two very familiar words. However, we haven't spent a lot of time looking at domain and range in terms of graphs. You've talked about domain being the x and range being the y, but now we're actually going to start applying them in terms of how do you visually see them and what do I do to an equation or to a function to actually find the domain and range. So first, let's make sure we know domain is the set of all x values in a relation. And remember, a relation is just a relationship between an x and a y, an input and an output. And range is the relation of a relation is a set of all y values, or now we're starting to call those y values your f of x. So it's your function that takes x as the input, and your range is your output. If you take a look at this example, the graph is showing the line y equals 3x, or 3 halves x plus 2. So it is a line with a gradient of 3 halves and a y-intercept at 2 right there. But notice this graph in particular, it could go on forever, but it's actually zoned in just to look at the y values between 8 and what is that, about 17 right here. Okay, so that means our y values are restricted. So we've been writing our y values as between 8 and 17 inclusive. So when we're particularly, we might want to look at just this set because it has to do with if this were representing money, maybe we want to look at just people who are spending a certain amount, or people at a bank who are only putting in a certain amount. Whatever the case may be, we might restrict our domain sometimes, and this is called a limited domain. So notice though, if we limit our domain, then our range is also limited, at least in this example. Because look at our domain. If we restrict from 4 to 10, then we track these points to the y-axis, and it also restricts our y values. So depending on what you restrict or what you're looking at, sometimes we might not have an open domain or an open range that will go on forever. So in this case, we're particularly looking for domain between 4 and 10 inclusive, and that also restricts our y values between 8 and 17. There are a couple examples here that I just want to take you guys to. So this first website shows you just a regular polynomial, but if you map the domain, so if you do go to this website and you wind up playing with the domain, notice how you're basically flattening out the graph, and you're taking all of the x values and you're trying to realize, okay, what x values are actually represented in this little piece of a function that I'm looking at. So notice we start at -3, and we have x values that go all the way up to +3. And when we're just looking at it as a curve, we might not necessarily see that. But if you think about flattening it out for the domain along the x-axis, we can see exactly where our x values are actually being represented. So from -3 to +3. So let's go ahead and flatten that out. And if we do the same with the range, we're really thinking just in the opposite direction. We're thinking vertically. So if I wind up smushing this graph along the y-axis, what y values would I be representing, or what would be represented in this function? So let's stretch it back out, and I'll pull it back in one more time. Notice that my lowest y value is down at, looks like about -1.5, and all the way up to almost 4, but not quite. So those would be my restricted domain and range in this case. So you're welcome to go to that website and try it yourself. On the second website from mathdemos.org, we're looking at a rational function at the moment. And notice how on the left you have the function, and this green marker is just tracing all of the domains, so all of the x values. And as this green marker traces the red graph, on the right-hand side, we're outlining in blue what x values were really being represented. So again, if you think about smushing the red graph flat along the x-axis, you would wind up hitting all the x values except for at 0, because at 0 we would have an asymptote. So coming to this website, there are tons of examples that if it's a little difficult to visualize what is happening when you're tracing the domain and the range from a graph, it'd be great to take a look through these different functions and see if you can practice until you get a sense of what is really happening here. So both of these are linked for you right here. So you're all going to pause here if you'd like to go to any on your own. All right, so coming back to our class examples, you'll notice that in example 2, we're given an equation, y equals 5x minus 2, and you're given the domain of -1, 0, and 2. So if I want to list ordered pairs, -1, 0, and 2 are already the x values. So I know that -1 will be substituted into my function, 0 will be substituted into my function, and 2 will be substituted into my function. So I am going to substitute in -1 so that I find the corresponding y value. So again, what I'm doing, I'll just write it out for one of them. What I'm doing is y equals 5 multiplied by -1 minus 2. And then that will give me my corresponding y value. Go ahead and take a moment and substitute in -1, 0, and 2 in order to find the ordered pairs. So for this example, we should have matched up with the ones that I have listed for you. And if you're asked to only list the range, we can list the range just as we've listed this domain in what's called set notation. So if I use set notation, I'll go ahead and use the braces, squiggly looking brackets, and the braces will hold all my y values that are corresponding with the x values for my input. So I'll include -7, -2, and 8. Usually you write these from least to greatest, but they're actually already written for us from least to greatest, so I'll go ahead and put them in the same order. All right. So these braces, the squiggly brackets, are what we're using to list a set. So anytime that we have to list a set of numbers, we use the braces. To be more formal, what you guys might notice is sometimes you're given, we'll talk about notation here for a moment, sometimes you're given a set of all y values such that y is an element of the integers. So that means they're telling you it's a z with a double line next to it. And this diagonal line, y such that, that such that just means you're describing y a little bit more particular, a little more specific. But then we're not including all integers. We're really just including when y is equal to -7, -2, and 8. And then we close our brackets. So sometimes you'll see a little bit more information in there, and that just depends on what you're being given. We could have done the same thing with our domain. We could have said x is a set of all integers where x is between -1 and 2, and that would have also represented all the integers that, well, actually, no, we're not including 1. So we would want to just list them as well, -1, 0, and 2. I couldn't say everything between -1 and 2 because I'm not including 1. Moving down to example 3, y is equal to x squared plus 3. So I have this graph, a quadratic, that starts as a vertex at 3, and then it goes upward, it opens upward. If I have the visual, again, think back to the 2 websites we looked at, it is really helpful to figure out what my domain is. If I were to flatten this graph down, so flattening it down all the way down to the x-axis, notice it has arrows on the end. So if I were going to flatten it down, it would actually flatten completely along the x-axis. It would include all these numbers right here that we see in front of us. But because it would wind up being a flat line with arrows on the end, because we're given arrows, it would go from -infinity all the way to +infinity. So you would actually wind up mapping every single x value that's possible if, because those arrows are telling you that it's going to continue forever. So for me to say that as my domain, I'll say that x is an element of all real numbers. So it's an R with a double line, and that stands for all real numbers that are out there. So -infinity to +infinity. You might also seen it written as an interval, where you start at -infinity and you go to +infinity. Now, if I use red for range, that means we're going to be smushing it along the y-axis. And if that's happening, I'll wind up with all my y values starting at 3. And it will go up because, remember, we'll have this line here with a big arrow. So we've got these 2 arrows that will now be coming in toward the y-axis. And our lowest value will be at 3, and then we'll go up to infinity. So again, we could have for range, y is an element of all real numbers, though, such that y is greater than or equal to 3. Okay? So sometimes you'll just see this part, y is greater than or equal to 3. That pretty much says all real numbers that are larger than or equal to 3. So that's the part that I would want to write for that one. And this is the part, for the most part, that you want to write for the domain. All right? This is a function. Remember, it does pass the vertical line test. So we talked about last year how if you have a function, I'll get rid of these lines here for a moment, but if you have a function, basically if you draw a vertical line anywhere on this graph, it should only pass once. So if I draw a line anywhere on this graph, I'll only wind up crossing my function one time. And that would happen anywhere. So if somebody else in the room drew a line somewhere else through this graph, they would still only cross once. That makes it a function, and it passes the vertical line test. So just bringing back a couple key items from last year. Looking at example 4, go ahead and try on your own what the domain and what the range would be. Notice that you have a point at 0, 0, and you have an arrow going downward on the right. So how does that affect your domain and your range? Go ahead and pause and try this one on your own. Go ahead and check if you agree. Notice the red for the range, blue for the domain. All right, example 5 brings us to one other topic that we just need to be considering as we get into more complex functions. Last year when you studied rational functions, remember that denominators are never allowed to equal 0. We have an undefined value when we try to divide by 0. So when we discuss what our x's are allowed to be or what our domain can be, remember that your denominator cannot equal 0. So we'll have to figure out when 2x minus 10 equals 0 so that we can say those x values are not allowed to be considered. So let's go ahead and think about that for a moment. Notice that you do have a graph of this function. So looking just at the graph, and you have your asymptote at 5, notice from the graph how this would flatten out with your domain and flatten out with your range. And go ahead and try this one on your own as well. So for the domain, x is an element of all real numbers such that the one exception is that x cannot equal 5. Notice that 5 is where our asymptote was. We also noticed that 5 came out as the value that we cannot have x equal for our denominator to not be 0. The other way is to list this as interval notation. So I start at negative infinity, and I can come up to 5, not including 5 though. The brackets mean not including, soft brackets, the curved ones. And then we can pick up at 5, and we can go all the way to infinity, but we just can't include 5. And you'll see a U between them a lot so that you can see how both sets come together. So it's the union of all the numbers between negative infinity and 5, and then everything from 5 to infinity. We're just not including 5 itself. And it might be hard to notice from the picture here, but we actually have a horizontal asymptote at about 1/2. And from last year when you guys were first introduced to drawing rational functions, that 1/2, when your degrees are the same in the numerator and denominator, comes from the two coefficients, so 1 divided by 2. So y is an element of all real numbers except at 1/2, because that's the one place that our graph does not cross. Just a reminder from a few years ago when you were first introduced to number line graphs, we can use the same notation for number line graphs as we were just talking about for our two-dimensional graphs. So here, if we're including 0, we use a solid dot. If we're not including, we use the open. So same thing when we start drawing our rational functions. If we have points, we'll use a solid dot. If we're not including values, we sometimes will use a dotted line for your asymptotes, just like you used an open circle for your number line. If you say the word between, we're not including. So -3 to 2. If I have all numbers between -3 and 2, I'm not including those two values, but I am including everything between them. And for our last minute today, go ahead and pause. Try exercise 2C number 1. For this graph, try to determine the domain and the range just by looking at the graph. Notice your x value starts at -1. Your y value, the highest one, is at 3. So make sure you've written yours the same way. If you wrote it in interval notation or with the braces, that's fine as well. And last but not least, consider this function, a square root of x plus 6. What values are you allowed to have underneath the square root? What would not be allowed as your domain? So think for a moment, see if you can decide what would be your domain, what would be your range, what kind of values come out of the square root for your range, and what kind of values go in for your domain. Go ahead and push pause and check your answer. All right, guys, go ahead and check your work. X should be larger than or equal to -6 in order to have a positive value underneath the square root. And anytime you take the square root, you assume the positive unless you're solving for possibilities. So for this one, y would equal positive number since we're taking the square root of whatever's inside. All right, have a good night. See you guys next time.